ancient Greece, the great mathematician Pythagoras established a school that was rigorous and progressive. You may be surprised to learn that he insisted that women be included in classes, even if they might not have shown great interest. Of course, Pythagoras is best known for his theorem of right triangles, where the sum of the squares of the sides of a right triangle equals the square of the hypotenuse. So, suppose we had a right triangle with legs of 1 and 2. Then we would get 1 squared plus 2 squared equals c squared, and we could calculate the hypotenuse to be the square root of 5. And Pythagoras thought that because the hypotenuse could be built, and because it could be constructed, that the square root of 5 was actually rational. Wait a minute. Whoa now. I hate to say it, but Pythagoras was wrong. So, it's up to us to clean up Pythagoras' mess and prove that the square root of 5 is irrational. We'll do this by using a process called proof by contradiction, which involves supposing the opposite of the statement, and that leads to something going horribly wrong, which means that the original statement would have had to have been true. So, let's start by supposing the square root of 5 is rational. That means that we could write it as the square root of 5 equals a over b, a fraction. To get rid of the radical, we can square both sides, and then apply rules for exponents. And we get 5 equals a squared over b squared. Finally, we multiply both sides of the equation by b squared, and we get 5b squared equals a squared. And let's focus on this equation for a moment. Now, it's common knowledge that any whole number can be broken down into a product of prime factors. That means that a can be broken down into a series of prime factors, and likewise, b can be broken down into primes. Note, we have to allow our imagination to see this as a nondescript product, not knowing how many primes we have, not knowing exactly which primes we have, not knowing if some of the primes in A are also found in B. We're thinking in broad strokes here. So, we'll substitute for A and B with these product of primes. And we get an equation where, again, we can apply some rules for exponents. And we show that 5 times a product of squared primes equals a product of squared primes. And this leads us to an unhappy ending, because if we count, we don't necessarily know the exact count, but if we, quote, count the number of 5s on the left-hand side, we know that we should get an odd number of 5s. And if we count the number of 5s on the right-hand side, we would have to get an even number of 5s. And that, my friends, means something has gone horribly wrong. We can't have an odd number of 5s on the left and have that equal to an even number of 5s on the right. So, the supposition was incorrect. Outwit, Grecian. Outwit, Grecian.